Hi everyone, welcome to the next video. It's been 2 weeks. I haven't uploaded anything for 2 weeks. Um, there's been some things happening, and I was busy with that. Okay, so coming back to what we were doing, so we built a basic web server to handle get, post, and put request. The next thing that I wanted to actually do was to go into a CVE, but before that, I would just want to show some basics of assembly and debugging. So I was thinking about it, like how I will actually go through the content. So here, what's the plan is to disassemble a few of the functions in the server and actually go through it in detail and see what all instructions are there, how you use GDP, uh, and things like that. If you don't know what a GDB is, it's the GNU debugger. You use that to debug programs such as s- web server program that we built to identify if there are any issues, is the program behaving properly or not. And there are a whole other set of requirements that GDB satisfies. You can do a search on it. Uh, but for the first thing being, let's just get started. So I have already made the server. So if I just run the server, it is actually running. It's already running on port 1337. This I was just trying out if everything is working properly. So if I just send the request, it's actually it's actually taking in the request, processing everything. It's doing what it is supposed to do. So first things first, I installed GDB. It's just like sudo apt install GDB. I think yeah, this is basically what I have to do it if you want to install it. And all right. So next thing is I want to add some basic things in the configuration of GDB. So how you do that is you go to the your home directory and you create a file called GDB init. I already created one, and I have added a few lines here. That is, first one is to set disassembly flavor to Intel. Uh, This basically means instead of showing the AT&T syntax, I'll actually be seeing Intel syntax, that is move RSP to RBP and things like that, instead of like having the percentage RSP. You can just look it up. It's much easier for me to read personally. Some people will like the AT&T syntax. Second line I have given is like to follow fork mode child, because our web server is actually handling multiple child process. I want to be following the child process to get to the main multiple functions. So if I don't put this on, GDB will just be stuck on the parent process and it won't do anything much. And this is another one to detach fork. So when the fork exits, I want it to detach so that it just won't get stuck there. And when the next request comes, I want to again want the GDB to follow the next child. That's kind of the idea here. Yeah, so I haven't written anything, so go back. um, I'm just going to initialize GDB with the server, so you have all of these details and things. Uh, the best way to learn assembly is to write your own assembly programs. The next best way I feel is to write C programs and disassemble it using GDB and see how everything works. Because you anyway wrote the program and it will be much easier for you to understand what's happening there. In this video, I won't be going through the entire program because that will be too lengthy. I'm just going to focus on particular areas of the program just to give you some conceptual ideas. First things, what are we actually analyzing here? Um, so just want to exit here. If you're new to this, you can just use file, and you can, if you check the server, this will actually check for the file headers and identify what the file is. It's telling me it's a basic L file, uh, and it's compiled use it's on GNU Linux and things like that. So these are information that you get from the header of this binary. That's a totally different thing. So let's go to the GDB. First thing, I'm just gonna since I know the program personally, I have the source code here as well. I know there is a main function in the main.c. So there's a command called disass, which basically means disassemble. You can use disass to disassemble methods. So I know I have a main method. And when you disassemble a main method, you can basically see the assembly instruction of how that method was perceived by the compiler. So the compiler is actually going through the code and compiling it. So the compiler made into machine readable code, which is assembly, and you can see the assembly code here. The very basics of assembly you can see right here, like any function that is being created will actually be represented in the stack. You can see it right here. This is the base pointer, this is a stack pointer. You can check it out, and this entire thing can be called as the these two lines plus there is a subtraction also happening. Okay, let me show you another method. So this is the main method. If you check our main method, that is right here, it has a start server, and it's doing that only. It's calling the start server that is in this particular memory address, that is 1332. We can also disassemble the start server method, see, and we can continue this. So in assembly it's gonna look really huge. This will look a bit complex, but once you get the fundamentals, it will be really easy for you to read. This is a good example of the initial start of a function where you are, whenever a new function is being created, your stack is getting reduced, not reduced, like your stack always grows to the bottom, like it's always growing to the bottom. So that is why you have a subtraction here. So your stack might only be here. So a new function comes, it's gonna get reduced again, and that's kind of how it, and once that function is over, it's gonna come back up. But how will it know where to come and where to go? That is where you have something called the function prologue and the epilogue. Really important concept. Uh, so this three line is the function prologue. You're pushing in the base pointer that is already there, and then you're saying you're putting in your stack pointer to your base pointer, that is it's pointing to the stack, uh, point to the top, and then you're reducing it. uh, and why are you reducing it? Because you will have all of your variables and your local variables that you're declared in your program, that will, you need space to store all of that. That is why you are reducing it. And it won't be like the exact space of your variables, because you need some alignment and padding for all of these variables as well. So it will be a bit more than that. So this is a start server program. If you check the start server program, the start server, it will taking some, but you know what, I'm not going to be looking at the start server. I think a much better function to be looking at is in the request handler. That is a handle request method, which has got a lot of things going inside of it. You have the comparisons and all of that, so it is a much better function to look at. So I'm gonna go back here. Sorry. I'm gonna disass the, what is the name of the function? It was handle request, right? Is there a handle request? Yes. Okay, this function is here, but let's make it more interesting. Oh shit. Okay. Let's put a breakpoint at handle request. So now I have set a breakpointer here. Now I'm gonna run the program. You can see the program has started and it is running on port 1337. I'm just gonna send a normal curl request. You can see it just got stuck over there because the program actually broke, and you are actually now disassembling it. Once this program continues in the GDB, you will be your request will get satisfied. Till then, it's all the information is kind of paused, and you have all the control over how the program flows. Now, if I do disass, you can see this small arrow on the left showing where the control now is. It's starting at the handle request. It's creating a new function prologue. That's it's actually growing the stack right now, like if you can see. So see, it's subtracting a huge number. Like when you see this, it looks so complex, right? See, it's a lot of things are happening. You, if you're looking at for the first time, you think it's super complex, but it's not that complex. Let's get the fundamentals clear here. So your stack pointer is being stored to your base pointer, and after that, so the function prologue, I was talking about the function prologue, and why I'm specifically taking this handle request method is because you can really see what is happening when there are a lot of local variables that you have declared, and how the compiler actually takes everything in and makes it into the assembly code. You can see the base pointer is being pushed in, it's been saved in, the next stack pointer is being moved to your base pointer, and you're reducing the stack by, it's sub means subtract, and subtracting the stack by around 680. And if you need to get some context on what this 680 means. So I'll take my friendly IPython 3. It's it's a good friend of mine. I use it for doing all of my basic stupid mathematical calculations. So it's a, I need to get the int value of the hex 680. So it, the int value of the hex value 680 is 1664, and it's subtracting it by this much of bytes, right? Um, and you might think, why is it doing that? 160 bits, right? 160 is 1664 bits. It's reducing it, and you might be wondering, why is it doing that? Why does it need to reduce it by that much? Then we need to go into our request handler and check out our handle request. This is the only function that we need to look at. This is what I'm going to be explaining throughout this video. You can see there are a lot of local variables that I have declared. There's a buffer which of size 1024, then there is a method of size 16, path of 256, host of size 256, there's a content type of size 64, then there's a content length. So I'm defining multiple local variables here. And if I'm just going to do a calculation of all of these, right? So if I'm just going to calculate, there are 1024 of that. I already did the calculation previously. Plus 64 plus this content length will be of the size 4 as well. So somewhere around 1604 is the size of all the local variables, and the rest is kind of the padding and alignment. If you don't know what alignment basically means, is integer is of size like 4. So, and if you're only having a number, you need to pad the rest of the bits. So it kind of calculates all of this in and like puts in a number there. That is what you see as the 1664 over here. Okay, now you have that basic understanding of why they are reducing the stack by such a big margin. The next thing is that they are taking a D word. You don't know what a D word is. So at even there are multiple word levels. So you have normal word, 2 bytes, then you have a D word, 4 bytes, then you have a Q word that is 8 bytes. Then there is something above that, and this thing still fight well. Uh, but at the very thing basic level, you can think D word and Q word. That is the only thing that you need to know about. And when you see this, right, D word PTR of your this is this is actually this representing a variable here, and something is moved into that. EDI is being moved into that. Okay, what is happening here? If you look at your program, right, you have a int socket in client socket that is an integer that is of size 4 bytes. That is why it's showing as a D word because it's not size 8. And EDI is the argument usually that's in the function. The first argument usually will be EDI RDI, and it's being stored into um, this variable right here. That's that's basically what it means. And the next thing you can see load effective address of RDX, and there is another variable here. If you look at the very next line, you can see a character buffer of 1024 that I'm declaring. That's basically what it means, creating a character buffer start index of, and that is being moved here. So it's going to start there. Next thing you can see is that I am setting the entire buffers each bits to 0 values. So I'm putting it 0. And now what is 0x80 that's happening here? That would be a good question to ask, because you're not there's nothing that is happening here, but the compiler always sees things differently. So all of these big chunks, right? You have 1024 bits of data that you're trying to store, and it should be split across. Okay, so there has been a mistake that I was saying bits and bytes. So this is actually, I should have been saying bytes. Instead of that I was saying bits. I don't know why I was saying that. All right, so 1024 bytes, if you split it by, let's first understand what in 0x80 is. It's 128, right? So uh, if you do 128 into 8, it's 1024. Now, what that means is that you have 128 chunks. It's being split into 128 chunks of 8 bytes, and so that it's easier for the compiler to put, or it's easier for, how do I put it in a good way? It's being split into 128 chunks. That is what compilers do when they are dealing with large data sizes. It always splits it into chunks and try to store it in like that. So that is exactly what you're seeing right here as well. Um, so it's telling that we are going to break it into 128 chunks of size keyword. You can see keyword, so it's size of 8 that is coming up here. And I think that's it. And now they are putting in the start of you know the buffer here, and REP stores keyword PTR of this basically means I'm actually putting the value as 0, right? So it's gonna put 0 to each of those bytes. So that is essentially what is happening. And these are other methods as well. Like I have method path, then host also I'm putting at 0, content type also I'm putting it at 0, content length also I'm putting at 0. It's zeroing all of these things out as well. So all of these are like zeroing all the bytes in the variables that I have declared. See, it's super easy once you understand the concepts. Um, Now moving on to this, I have this read function that is here happening here. So client socket buffer size of, see, now if you think in that sense, it's taking in the buffer. the size of the buffer, and mm, and the client socket, and so basically that's it. And now it's reading the read. And at PLT, so see, these read functions are taken from other system level, other C libraries. So uh, that those functions are not essentially written in this program, right? So at PLT basically means, I think it's program linkage table. So there's a linkage table when you're running the program, that when you're running a program and you're calling from other system libraries, other C native libraries, at PLT will check the read. At PLT will, but means that you will go to the PLT table and check for the read, and that's it. So then all of the definition declarations and definitions of that read will be there in that. uh, that is how everything works. That's kind of how the assembly code looks like. Now I want to show you some features of GDB real quick. One cool way to look through these. So if I just do NI means next instruction. So now I don't even know what is happening here. So if you press Control X and press 1, okay, why is not that happening? Yeah, I think it's Control Shift and X1. You have the source thing, and if I Control Shift X and 2, strange, Control X and 1. Control X closes this. This is an interactive layout that I have. Controls X 1. Oh yeah, Control X 2. Now if I do, so what I did was Control X, then I press 1 and 2. 1 is for the assembly and the source. 1 and 2 shifts between the assembly and the source. So now if I do NI instructions, this is what I want to have. Control X. Okay, this Control X and A, I close it. Control X 1. I have the assembly. Control X and 2. Awesome. So now I have the register list at top. Now if I do NI, I'll have the assembly instructions that happens right below that. NI means next instruction. So I'm stepping one instruction at a time through the code, and you can see what are the differences in each of the registers that are there. So I can do NI, and I can keep writing it like that, going like that, and seeing what are the changes. See, okay, so now I want to go back. So that is one thing to keep in mind. And say if you want to break somewhere over here, and how can you do that? There are multiple ways to do it. You can put a breakpoint using this memory address, or what I would like to do is that, so I am in this particular program, right? And it's in the method handle request, and I can just put in the line number. What is the line number? It's 1073. So 1073. So now it breaks, right? You can check the memory address. So it ends with 5974, 5974. So you can see, I think there's something called show breakpoint as well. Show breakpoints. Is it info breakpoints? Yeah, so if you type in info breakpoints, you can see where all your breakpoints are essentially. And you delete breakpoints as well. You can delete 1, 2, or 3 to delete the particular breakpoints as well. I think that itself covers some of the details of this assembly. Um, yeah, and I think that should be enough for this video, because this is just a small video that I want to create just to showcase assembly. Uh, to try this thing out on your own files and see how everything behaves, because it will give you a good understanding of assembly as well. Great, thanks for watching. Bye.